Well, we're on to chapter 11, which is states of matter. Let's talk about a few concepts and definitions that you probably already know, but let's just make sure you're solid with them. I put here on the board gases, liquids, solids, the different states of matter, and we know that when a solid becomes a liquid, that is called what? When you're heating up a solid to become a liquid, that's melting, or fusion. It's another word that we sometimes use is fusion. So all of these processes going in this direction, they're all endothermic. You have to put heat in. When a liquid becomes a gas, that's when the liquid vaporizes and becomes a gas. At the point of boiling, it's called boiling point. Here at the point of melting, it's melting point. Um, this direction, solid all the way to a gas, bypassing the liquid phase entirely, that is sublimation. You've done that in lab with the ammonium chloride. Um, Also an endothermic process. These on this side, these are exothermic processes. When a gas condenses or deposits and directly and becomes a solid without going through the liquid phase, that's called condensation or deposition. A gas just down to the liquid phase is condensation, and obviously a liquid that becomes a solid is freezing. Okay. The freezing point and melting point, same temperature. Boiling point, condensation, also same temperature. All right, the term vapor pressure, where does that come from? Well, all liquids are constantly vaporizing. Okay, they're always vaporizing. The molecules on the surface of the liquid are always escaping and becoming vapor. Well, if you've got a closed container, that vapor that's being produced on top of the liquid, you can actually measure that pressure. That's got the vapor is just hitting the sides of the container, and that's called vapor pressure. So vapor pressure is very temperature dependent. As you increase the temperature, the vapor pressure increases. Why? Because more molecules are moving, more liquid molecules are moving and escaping into the gas phase. So vapor pressure increases as you increase temperature. Right here, as temperature increases, vapor pressure increases. Vapor pressure is the partial pressure of the vapor over the liquid at equilibrium at a given temperature. Okay, and we have vapor pressure, temperature tables in the lab manual and in the textbook. Okay, if a liquid has a very high vapor pressure at normal temperatures, let's say at room temperature, that means that liquid escapes and becomes a gas very, very easily. And the term for that is a volatile liquid. Let me see here, bring this down a bit. This is a volatile liquid. So volatile liquids are liquids that very easily escape into the atmosphere and become gases. All right, two terms that I have written down here, boiling point and freezing point. Let me give you a textbook definition of boiling point. This is the temperature at which the vapor pressure of a liquid equals the pressure exerted on the liquid. So when if it's just to the atmosphere, if it's just regular in a pot boiling, let's say, then the pressure exerted on the liquid is the atmospheric pressure. But if you're like doing it in a vacuum, then the pressure exerted on the liquid is whatever you've got in that vacuum setup. But let's say we're talking about atmospheric pressure. So the boiling point of a liquid is when the vapor pressure of that liquid is equal to the atmospheric pressure. There's a term called the normal boiling point. Normal boiling point is at 1 atmosphere. Okay, so if we're talking about water, we know that the normal boiling point of water is at 100 degrees Celsius at 1 atmosphere. Okay, what's freezing point? Freezing point is the temperature at which pure liquid changes to a crystalline solid. Now, we're not going to be dealing with a lot of the solid part of this chapter, the crystals and all of that. You can definitely read over it, but you should know the term freezing point and you should know the term melting point. They're at the exact same temperature. Okay, now freezing point and melting point don't get affected by pressure, while boiling point definitely does. Okay, all right, now let's get into the process of changing phases. So you know that if you take a solid and you melt it, and then take that liquid and boil it, you're going to have to apply heat. Well, there's actually an extra bit of heat you have to apply in when you're at the melting point and you want to switch it from a solid to a liquid. That's called the heat of fusion. So you're at the melting point, but it's still a solid. Well, how do you switch it from solid to liquid? You add extra heat in. Also, the boiling. Let's say you have a liquid and you heat it up, and now it's at the boiling point, but it's still a liquid. How do you switch it from the liquid phase to the gas phase? You have to add an extra bit of heat in, and that's called heat of vaporization. So those two things, heat of fusion, which is the heat to switch it from a solid to a liquid, that melting, and heat of vaporization, they're under the big umbrella category called heat of phase transition. Heat of phase transition, because you're transitioning from one phase to another. Remember, for the heat of fusion, you're already at the melting point, so you're not changing the temperature. All you're doing is changing the phase. So delta H of fusion, delta H of FUS, which is fusion, okay, this is the heat needed to melt 1 mole of a pure substance at its melting point. So you're not ever changing the temperature when you're doing this phase transition. You're already at the melting point. I'll give you an example here. When you have water that is a solid, and then we're going to turn it to water that is a liquid. Now we know that the freezing point and melting point of water is 0 degrees Celsius. So let's assume we're at 0 degrees Celsius. We have an ice cube and we're at 0 degrees Celsius, and we want to turn it into liquid water at 0 degrees Celsius. How much heat do we need to put in? Delta H of fusion, for this is not a number you need to memorize, is 6.01 kilojoules per mole. Okay, this is to overcome all of the bonding in a solid molecule. So you got to break all those attachments and allow it to become a liquid. Okay, if you crunch the numbers, I think it's like 333 joules per gram, if I'm not mistaken. But you will always be given the delta H of fusion or the delta H of vaporization if you're doing a problem. And we're going to be doing a bunch of problems in a minute. All right, delta H of vaporization. Let's make sure you can see this. This is vaporization. For this one, we are at the boiling point, okay? And we are at the boiling point, the boiling temperature, but a liquid. We need extra heat in, which is called the delta H of vaporization, to switch it from liquid phase to gas phase. So delta H of vaporization is the heat needed to boil 1 mole of a pure substance at its boiling point. BP just stands for boiling point. Okay? Let me give you that example for water. You know what, guys? I'm just I'm going to erase this. We're focusing on delta H of vaporization now. Okay. We have water that is a liquid, and now I want water as a gas. So in this scenario, we're at 100 degrees Celsius, but we still have water as a liquid, and we want it to escape the liquid phase and become a gas. How much extra heat do we have to put in? Delta H of vaporization is equal to 40.66 kilojoules per mole. Look how much more energy is needed to get those water molecules that are liquid to escape into the gas phase. A lot more than is needed to get the water molecules that are ice to get into the liquid phase. So going from liquid to gas requires a lot more energy. And if I remember correctly, it's like 2,260 joules per gram. And this is only 333 joules per gram. So, and you can just compare the kilojoules per mole. You can see this is considerably more over here. Again, all those intramolecular forces, all the hydrogen bonds that are occurring in the liquid phase, as you're trying, you have to break all that so that it can go up into the gas phase. Okay, let's do one quick problem, and then we'll end this video, and then the next video we'll do a whole bunch of more problems, calculations to get you through this portion of the chapter. All right, so let's say you are given that the heat of vaporization of ammonia, so delta H vaporization of ammonia is 23.4 kilojoules per mole. So the question is, how much heat is required to vaporize 1.00 kilograms of ammonia? This should be a pretty straightforward, simple enough problem for you guys. All right, so we'll just write, here's 1 kilogram. 1 kilogram is 1,000 grams. You could, switch it right away or set it up. 1 kilogram is 10 to the 3 grams. Metric conversions. Okay, you're going to have to convert your grams to moles because they gave us the delta H of vaporization in kilojoules per mole. We can say 1 mole of ammonia is 17.0 grams of ammonia. Okay. And then we're just going to use this guy over here. 23.4 kilojoules per mole. Our moles will cancel. We do the math. 1 times 10 to the 3 third, which is 1,000 divided by 17 times 23.4, and round it to 3 sig figs. I can't tell if my handwriting is right. It's either 1.30 or 1.38. Let me just write it down as an 8, and then I'll double check right now. It's kind of sad when I can't even read my own handwriting. Okay, where's my calculator? Here it is. Hold on 1 second, guys. 1,000 divided by 17 times 23.4 is, 1.38 times 10 to the third. Yep, that is it. Okay, good. So the next video, we'll do a few more of these types of problems, but kick it up a few notches. Okay.